Okay, so how does power series and differential equations come into play? So this is one of the probably worst ways to solve for differential equations just because, well, if you like series, it's probably your favorite, but not a lot of people like series in general when it comes to it, and they're very lengthy. It's not as smooth as Laplace or any other method itself. But before we actually do this, we have to do, again, a very special definition of the analytic part. So a point x naught is called an ordinary point of the equation, or of a differential equation, equaling 0 if both p and q are analytic at x naught. Okay. So remember, analytic means there is an interval where is a radius of convergence in. So if x naught is not an ordinary point, it's called a singular point. So basically, we got to figure out, where those points are. Probably you get rid of them, or you can't use them all itself. Okay. Define singular points, or if something is analytic, is not as obvious as we think. So we'll just do an example so you can see how that's going to work. So we want to determine all points where it's singular. Basically, it's not ordinary point or not analytic at that point. So the first thing we're going to do is we're going to divide everything by x to make it in terms of this. We want it roughly like that. So we identify p and q. So we're just going to divide by x. So if I divide by x, we now just get oh, it's -1. Let's put over 1. That. Okay. Okay, so now it follows the same process we have up here. So we have step 2 now. So now step 2 is just identifying our p and q. So our p in this case is always next to the y prime, which is the 1 over 1 minus x. And then q is the one with no derivatives next to it. So it's just the simple y. So it's just the sine x over x. Okay. Now, third step is we want to figure out where it's singular. So it's singular based off this definition. It's very vague, right? It says so if both p and q are analytic at the point. So we want to see is when is both p and q fail to be analytic. That's what we want to figure out. So how do we do that? Again, not as obvious, and it's a weird definition. Analytic points is, I guess, vague when it comes to it. But in layman's terms, what they really want you to say is it's analytic everywhere except when the denominator equals 0. Basically, the domain. I'm not really sure why that's really put, but they should just really just put that in the definition. So basically is when the bottom equals 0, right? So basically when 1 minus x equals 0 and when x equals 0, right? Those are the both portions there. So on p of x, this is true when x equals 1, and for q of x, this is when x equals 0. Okay. Now you may think, all right, that's done when it comes to it, but this is where this is a bit tricky. Because we're dealing with power series, and analytic represents a power series itself by the definition, let's go to the power series of sine of x. Okay, so the power series expansion of sine of x looks like this. And it's because it's sine, it's the odd powers themselves. Okay. Now, in this one, I am dividing by x. So if I divide everything by x, this just ends up being 1. This just ends up being, well, remember, you keep change flip. So this ends up being now the even powers over the same odd power factorial. So really, this is not actually true because I am never non-analytic because the denominators will always have constants. So really, it's actually not here as well. So it's only there. A subtle little, kind of thing. That's the reason why power series are really tricky. Okay. But let's suppose we know how to do this now. We know how to get rid of analytics. Let's suppose everything is beautiful. Meaning, let's suppose everything is analytic. We don't have to take them all out. We just have it itself. Okay. So the question is, how in the world do we solve using the power series? Okay. And that's one of the most difficult parts of this portion. Okay. So again, the reason why we talk about these new definitions is we want to find p of x and q of x, and such that we can just get rid of the ordinary points and somehow solve for the differential equations using the neighborhood of x naught. Okay, and we'll talk about that x naught in the neighborhood as we go along into an ordinary differential and a basic differential. Believe it or not, this is actually a simpler of the multiple we can actually deal with. Okay, so here we're just going to talk about the actual wording. So we want to find a power series solution at x equals 0 to this. Now what this is saying is x naught is equal to 0. Okay, that's what our definition. That's what we're dealing with here. Okay. So let's write some stuff down. So we have y prime. So we have p of x is equal to 1. Q of x is equal to 2x. And again, this is nice because this is analytic everywhere. This is never 0, and this is also, well, x could be 0, but we're good because, don't get something that's undefined. So basically, in other words, we could find a power series that makes this work. That's pretty much what this check is all about. Okay? Fancy word for saying that. All right, so now that we can actually solve it, let's actually try this out. Okay, so according to our power series, this is our goal. And then remember, this is x naught, and they're told me x naught is going to be 0. This is going to be our solution. Okay, so actually we're almost done. Pretty much the entire work of using a power series and solving for a power series is finding this constant, this coefficients of them. That's what we really care about. Okay, so if this is just y naught, so that represents y itself, we now have to find y prime. So, plug it in and eventually do all that fun stuff itself. Okay, so since it's y prime, we're just going to take the derivative. So y prime of t is just the derivative of this portion. And I'll keep it at 0 just for including the same indices. Okay, so now I just plug it into here. I guess how do I want to do this? Let's say this is step 1. This is step 2 now. Okay. All right, so step 2, we insert all of this using its power series conversion. So y prime is just this. Well, not just that anymore, but this mess. Plus 2x all right, so this equals 0. Let's talk about this x. So x, this series is in terms of x. So if I multiply this entire series by x, what does that mean? When I multiply, that means I add powers, right? So what this ends up being is this becomes technically n plus 1. Okay. Now, this is when it comes to step 3, I guess if you want to call it. We want to have all the same indices. Okay, so here I have n minus 1, and now here I now have n plus 1. So what I'm going to do is I'm going to change the indices of each individual and just have it as x to the k power. I don't care about the starting points, but I want to have the same indices because I want to put them together somehow into one single sum. So over here, we're going to have k equaling n minus 1. And over here, we'll have k equaling n plus 1. So in this case, this is going to be n is equal to k plus 1. So if I want to rewrite all of this portion, I'll just do it up here. So this becomes k plus 1, yeah. Yeah. I'll start at 0. So ace of n, so ace of k plus 1, x to the k. And if I do the same thing here, so I subtract it, so n is going to equal to k minus 1 this time. Yeah. So add it over here. And I'll put this 2 on the inside now too, so it'll be 2 times ace of k minus 1 to the x to the k. This whole thing equals 0. Alright, so like I said, I want to put these together. They have different indices. So, well, if k equals 0, so let's say this is step 2, so this is step 3. So if k equals 0 here, what do we get? So x to the 0 power is 1. We just get k plus 0 plus 1 is just 1. So we just get a 2. Right? Because n is, yeah, n is 2. Okay. Oh, sorry, not 2, 1, right? So I'll just write it. So if k is 0, so we get 1. Ace of 0 plus 1 is 1 times x to the 0 power. So this ends up being a first. Okay, there we go. So now I can put these together by doing a1 plus the sum of k equaling 1 now of these put together. Now, I'm going to factor these out and have these together. So it kind of looks like this. There we go. All right. So now we got to figure out the main part. What are these? And that's a bit of a pain. Okay, so let's do step by step. So let's see what we have. All right, so this is where it gets a little finesse. Because these two add up equals 0, we can say, well, that means ace of 1 is 0 and this sum is 0. Or more precisely, that equals 0. Because again, all we care about is the coefficients. Obviously, these are going to be powers, but we care about the actual coefficients of them. Okay? So all of this somehow has to end up equaling 0. Okay? So we got to solve for something. We already have an initial condition, so we could solve for one of these. So we're going to solve for this coefficient here, let's say. So that means subtracting this over and then dividing by the k plus 1. So this is on top. Oh, it's minus. And I'll put this at the bottom. And I'll put this to the side. There you go. So times. Okay. Okay, so why don't we look at some terms this looks like. So for example, if k equals 1, we have a2. Again, k equals 1, so this is a 2. Times a, if k equals 1, we have, yeah, equals 1. This is a naught. And let's keep going. So a3, so this is when k is equal to 1, k is equal to 2, this is a 3, k equals 2, so that's 3, k equals 2, that's a 1. I'll do a couple more. So 3 minus 1, so a3. Okay, so we know this. So that's here. This is 0. So therefore a3 is 0, which is right here, which means a4 is 0. Well, isn't this interesting? Okay. So it looks like a couple terms actually just go away, right, which is kind of nice. So all we're going to do now is somehow shuffle stuff away. Let's see, so how do I want to say this? Oh, I see. Okay, I know what I do. Okay, so all of the odds will eventually just go away. Now, if you're wondering, well, how does that make sense? Right, this is 0, this is 0, 0. Well, let's go. This is the one we don't know. Here. So this is the same process as that, right? It just doubled. So this can be the same process. I can manipulate this to make it just be a2. This one over here, I can manipulate this to be same process, over and over again. This is now a 3, right? And forward and forward and forward and forward. Okay. Now, how does this work? Therefore, if I want to rewrite all of these processes, so getting rid of all of the odd powers, so all of these odd powers and so forth, we get a naught, which we don't know, plus a2 x squared plus a 4x to the fourth, and we keep going. So, what does this look like? So, this ends up being a naught plus this sum. Well, this sum well, let's do, sorry, let me just do one step just in case you guys aren't sure. So this is a naught plus, and then how does this process look like in series notation, right? Going back to what we have. So this a4, if we go back up here, oh, it's actually right here, sorry. Where's a4? Here. Becomes this fraction, becomes this fraction. So how does this series comes into play with these coefficients in front? So this is -1, this becomes -1, and well, if you plug that in, it gives you a positive, right, and so forth. So it flips sign. So this becomes a sign change of some sort. We are dividing by some factor of 2, which becomes 2 factorial. And since we only want the even numbers, it's going to be x to the 2n. So in fact, that is our sum there. So this would be our answer. Isn't that a beauty? So let's try one more. This time find the general solution. Okay. So again, it's a power series. Okay. And we're going to use x naught to be 0. So therefore, y of x is equal to this power series, just like we had before. All right, so first derivative. And since we want two derivatives, second derivative. Gives us that. All right, so now we go to step 2. Plug in everything we have so far here. So it's going to be 2 times y prime, so this sum. And yeah, I'll get rid of all of them. Okay, times this x. Should I put it in? So yeah, I'll put it in. So again, just like the last example, this x times this one will be adding it to it, so it just becomes n. There we go. Okay, now just like the last example, I want all of these indexes to be the same. Okay, which is nice since these are already the same here, which is great. So we could put these together. So this one I would say let k equal n minus 1, so therefore n is k plus 2. So if I rework this, so n is hubering over, so you have k equaling 0. And for both of these, I'm going to let k equal n, so that we'll have all the k values themselves. So k plus 2 minus 1 is just k plus 1. Oh, they don't have the same indices. Okay. Oh, these two, 0 and 0. Okay, that's nice. Okay. So now we're on to step 3, is breaking this apart. So you want, again, I want all the indices to be the same now, or all the summation parts. So this is 0, 0, so this is the only one we got to deal with. Okay. Oh, actually, let's have all the indices to be to 1. So if k equals 0, we get a squared, or sorry, not a squared, a to the second power. This is 2, this is 1, so 2 times 1 is 2, times 2 is 4. So we get 4a2. This one doesn't have a 0, and if I plug in 0 here, I get a of 0. So plus now all of this summation put together, starting at 1. Okay. Alright, so again, I'm going to put everything and this to the outside. Okay. So now, just like last time, coefficient is what we care about, so this and these all have to be 0, right, or end up equaling to 0. So we know that 4a2 plus a naught equals 0, and this whole sum also equals to 0. Okay. Alright, so now again, just like last time, we're going to solve for an index C, and we're going to solve for this index right here. So bring everything literally to just to the other side. Okay. Alright, so this I could put together. So I'll make this the k plus 1 times ak. So just they have a common one, so that'll be easier. So this is a plus, so I'll subtract it over. Do I want to do that? Yeah, I want to subtract it over. So bring this to the other side, and then divide all of this to the other side. So we have, okay, so minus all of this. So we're going to have minus divided by all of this. And notice the nice thing is at least something cancels. So it's not as insanely difficult that it actually looks like. Still difficult, but still. Okay, so now at this point, we have to do what we did again last time, is break it down into portions. Okay, so we know this equals 0 from one of our situations, right? So if I just bring the other side, so we know that 4a2 equals negative a naught. All right, okay. And now we're just going to do situations. So we have 0, so we start at 1. So if k equals 1, what do we have here? So if k equals 1, we have 3. K equals 1, this is 3, 6, so negative 1, 6, a1. Okay. K equals 2, this is 4. Alright, so this is going to be, this is 2, so 4 times 2 is 8, a2. Okay. Alright, we'll just do one more. 3. This is going to be 5. This is going to be 5, 10, a3. So if you notice, it has a little bit of pattern on the bottom. Okay, that's kind of it. So let's make this look kind of like this. So if I just divide this by 4, that means a2 is equal to negative 1/4 a naught. So this is technically k0. So we kind of see a little bit of a pattern going forward, right? We're just adding to each individual case going down the list. Okay. All right. And hopefully you know, and something that we gotta notice when it comes to these kind of series is I can replace, well remember, so this is times a2, and a2 is this, right? So it's actually more advanced because this is actually multiplied by another negative 1/4. So this becomes positive 32. And this one goes here, so all of this goes there. So this becomes also positive 60, right, times a1. So a lot of it's dependent on its previous terms, right? So this can go here, this can go there, and it follows that same pattern of even and oddness itself. Okay, so again, after a lot of algebra, the even a's is always dependent on technically just a naught going forwards and backwards. So the a naught's portion is going to be plus or minus over the fraction of 2 to the n squared times n factorial times a naught. That's that, you know, a sequence that keeps going. And then the odd powers follows about the same process, but believe it or not, it goes on the bottom is just going to be the odd number because it's multiplied by 3 or 5. Keep going. So same thing, plus or minus on top. This time 2 to the n and times 2n plus 1 times a 1. Now, because these all together give me the entire sequence of itself, so therefore we actually have two equations, or two solutions, or two, the general solution is the sum of both of them put together. So it basically is the sum of all of these. And then the other one is just the odd power. Now, you may ask, oy vey, yes, power series is not the funnest to solving for a system, and it's really just because of this. You have to find a pattern that works, repeated, and that's not fun to do. And then really at the last step you want to, if you really want to do so, is somehow you can be able to convert these to what we know. If it's like a sine, a cosine, ln of x, or some e to powers. Most of them you can't do so. It's just a unique one. But sometimes we have an actual special one where it can be converted to like an ln of x. So it's a power series of the ln of x, and so therefore ny is some power of squared or something like that. You can convert it to its, manipulate it, but, that's just another mess to deal with, right? That's another question just to tolerate that kind of situations. But yes, so hence the reason why I put more pain. This is not fun to deal with itself. But it is, another alternative and another method to solving for a differential equations situation-wise.